What's up, my Precalc people? Michael Porinchak here. In this video, we're going to tackle topic 3.2 and 3.3, sine, cosine, and tangent, and those values. All right, now listen, this is the beginning of trigonometry, and trigonometry for a lot of students is very, very difficult, so I want to try to make it easy by not actually starting with sine, cosine, and tangent. You might be like, what? That's what this topic's about. Yeah, that's part two. This is part one, and in this part, I'm simply going to explain the setup, because the definitions for sine, cosine, and tangent are very long in particular, and they are filled with tons of big new vocab words. So if we just understand the setup, what an angle is, how to draw an angle in the coordinate plane, how to measure an angle. Once we learn all that, then understand the definitions of sine, cosine, and tangent are going to be a lot easier. So stay tuned for what actually the definitions of sine, cosine, and tangent are and how to actually find the values of them. That's in part two. This part one video is just making sure you understand the setup for what the heck is the foundation for trigonometry. Trigonometry is all about the study of angles and triangles and circles and connecting it all together. And if you don't understand the beginning, the basis, the foundation, the setup, you're never going to understand trigonometry. So please watch this video. Hopefully it makes a lot of sense. Replay the key parts if you need to. Then check out part two where we actually define sine, cosine, and tangent and talk about how to find the values of those three trigonomic functions. So the first thing we're going to do, if we have to understand trigonometry, is we need to break down what the word trigonometry even means. So it's basically broken down to a prefix, a root word, and a suffix. So let's talk about the prefix. The prefix is tri, and tri means three, and this is referring to three sides of a triangle. The root is gon, and that actually means angle, and then the suffix is metri, which means measurement. So the actual meaning, combined meaning of these three things is the measurement of triangles or the measurement of angles in triangles. That's what trigonometry is all about, looking at the angles and measuring the angles inside of a triangle. All right, so to fully understand the definition of sine, cosine, and tangent, you must first understand the setup for the scenario. Now, this is where a lot of kids think, well, I know what trigonometry is, or I can understand it, or maybe some kids actually really struggle with trigonometry because they don't understand this setup. So that's why I want to spend a lot of time in this video just making sure you understand the setup for the foundation of trigonometry. So here it is. In the coordinate plane, an angle is in standard position when the vertex coincides with the origin and one ray corresponds with the positive x-axis. The other ray is called the terminal ray. Now, I highlighted a lot of the key words in here so we could break them all down to fully understand what the heck this setup is even saying. So let's first start off with the first word, and that is the coordinate plane. The coordinate plane, you should all know, is the traditional XY axis, right? Where we have points, and on the coordinate plane, a point has an X coordinate and a Y coordinate that tells you how far on the X axis you are, positive or negative, and then how far on the Y axis you are, positive or negative. Now, the next most important word in that definition is an angle. So an angle consists of a vertex and two rays extending from that vertex. I hope you remember this maybe from geometry class. So here it is. Now, we named the two rays. The first ray is called the initial ray. That's the ray where the angle starts. And then the ray where it ends is called the terminal ray. The word terminal means end. So this angle here would start at the initial ray and go to that terminal ray just like that. And we see the vertex. Now, if we go back to that definition, it says an angle is in standard position when the vertex coincides with the origin. So that's why the first thing I did here was I put the vertex at the origin. And one ray coincides with the positive x-axis. So that's the initial ray. So the initial ray is always starting on that positive x-axis. It cannot start anywhere else. Then the terminal ray is the other ray where we end our angle. Now, the initial ray cannot change, but the terminal ray can rotate based on the angle measurement. So, for example, this one starts at the initial ray and it goes all the way here to the terminal ray. Now, we have the fact that the angle could rotate as far as it wants. So most kids think back in geometry that the biggest angle you could be is 180, but in trigonometry that's completely false because we could start that initial ray, we could go all the way to 90 to 180, and then we could continue even on to that terminal ray right there. So the angles can again rotate as much as they want. Now, we could even rotate further. So check out this example here where we continue to rotate all the way around into quadrant 4. The most important thing is the initial ray starts on that positive x-axis, the vertex is at the origin 0, 0, and the terminal ray goes wherever the angle tells us to go. Now, we actually have two types of angles. The first type of angle we have is a positive angle. A positive angle rotates in a counterclockwise rotation. So we actually have to add that arrow in showing the direction of our rotation. So if we start from that initial ray on the positive x-axis and we start going up, that's rotating in a counterclockwise rotation. That's going to create a positive angle. All right, here is another example where we continue on. So again, we're rotating in that counterclockwise rotation. That's that positive angle. But what's cool is that we're not constrained to rotating one revolution around. We could actually continue to go. So if we look at this example here, we see that we actually started and we went all the way around one full revolution, all the way around another revolution, and then all the way around another revolution, and then even a little bit more. So what this allows us is to have angles that are infinite, right? Angles can keep rotating around and around and around and around and around. They can go as many times as they want. Just keep rotating and rotating and rotating and rotating. Now, obviously, they could repeat themselves, right? Because they could rotate all the way around and then all the way around again and so forth. But that's the idea that allows angles to be infinite. There's no restrictions. The domain of our angle values is now infinity, right? It could be anything we want. We just keep rotating around. Now, we also have negative angles. Negative angles simply rotates in a clockwise rotation. So again, we're starting on that positive x-axis. The initial ray has to start there. And then we're rotating down. That's going to create a negative angle going in that clockwise rotation. So here's an example of an angle that's rotating downward to get there. And that's where we're going to end our terminal ray. And that, of course, creates a negative angle. But just like positive angles, negative angles can go around and around as many times as they want, as long as the initial movement is in that downward direction. So this angle started going down and went all the way around again, all the way around again, and then it continued and down and back into quadrant 4 there. So again, it's the direction of that angle starting. In this case, it's starting going down in a clockwise direction. That's going to create a negative angle. So again, this allows angles to be literally any number out there. Negative infinity to positive infinity. Angles can be as big or as small as you want. All you got to do is continue to go around and around and around and around and around. Now, any terminal ray can be gotten to by using a positive or a negative angle. So think about this. So here is the initial ray, of course, starting on the positive x-axis, and a terminal ray that I have ending here in quadrant 3. But I could get to this angle using a positive or a negative angle. So here would be a positive angle going in that counterclockwise direction, or I can also have a negative angle that goes in that clockwise direction right there. Notice that they both ended at that same terminal ray, just two different ways to get there. So there's two different angles that end at that same terminal ray, one being positive and one being negative. Now, there's the positive and there's the negative angle. Now, any two angles that arrive at the same terminal side are said to be co-terminal angles. So co-terminal angles are two angles that have the same terminal ray. So this would be a great example of two coterminal angles, one being positive and one being negative. Now, here's another thing that I would add on top of that is that any angle actually has infinite coterminal angles. So let's talk about this. So here is an angle that ends in quadrant 2. So we have a positive angle right there that gets to it. And then we also have a negative angle that goes like this. Okay, you see those two angles, but there's actually more angles, right? I can make another positive angle. Another positive angle would go all the way around, one rotation, and then go, well, I don't know what happened there. It would go all the way around and then end at that same value. So again, there's actually infinite coterminal angles. Angles in standard position that share a terminal ray differ simply by an integer number of revolutions. So what I mean by that is, again, there's that first positive angle, right? But if I go one revolution more, so there's one revolution and then that same original angle, I don't know why this program keeps trying to make me a circle there. But if I go all the way around that one revolution and then I go that same original angle, hey, look, I got a coterminal angle because I got two different angles that differ simply by one revolution, but they end at that same terminal side. And you can even do this in a negative direction as well. I could go like this. There's a negative angle right there going in that clockwise direction, but I could also make a negative angle that goes all the way around and then back there. The difference between those two angles is simply going one more revolution all the way around. And I can even do more, right? Like I could go 5 revolutions and then back to that terminal ray. So there are infinite coterminal angles. So if you find an angle, there's infinite coterminal angles that arrive there. All right, so now hopefully we have a good idea of the setup, right? We have an angle, vertexes at the origin, initial rays of the positive x-axis, and our terminal ray ends wherever it wants to end. And then we could have the angle that gets us there, and we could get a positive angle, a negative angle. We can go around and around and around, backwards, forwards, however we want to do it. Okay, now that we understand the setup for an angle in center position, how do we measure such an angle? Well, let's first talk about labeling angles first. So first we want to label angles with variables if we do not know them, right? If you don't know something in math, you use a variable to label it. So you can use x, w, a, or b, or any variable you want. But in trigonometry, it's common to use Greek letters since the Greeks kind of founded trigonometry. So typically you'll see Greek variables like theta, alpha, beta. I know they're kind of weird to draw, but there's an example of those Greek letters. So what we'll do is we'll say, hey, check out this angle right here. Look at that positive angle, and let's call that angle theta. Now you could use a, or you could use x, or you could use w if you really want to, but we kind of pay homage to the Greeks and use Greek letters like theta, alpha, or beta. All right, so how do we measure an angle? So if we look at that angle that I just drew right there, how do we measure it? Well, the most common thing that a lot of kids want to go to that I kind of already mentioned or alluded to a little bit ago is degrees. And that's very, very common, but there's a problem with degrees. So the issue with degrees is that, 1 degree seems like arbitrary or random. Like, who invented 1 degree, right? Like, what is 1 degree? Why is 1 degree 1 degree? How did 1 degree become 1 degree? Like, and who decided there was 360 degrees in a circle and not 400 degrees? So degrees are something that you guys have been working with probably since you were very young, maybe even 2nd, 3rd, 4th grade. But the problem with degrees is that it was just a measurement that somebody made up, and it doesn't really have any direct connection to it. So we're actually not going to use degrees at all in AP Precalculus, like never. We're going to use a different measurement of angles that is probably very new to you called radians. Now, this is just going to add another layer to trigonometry that makes it a little bit more difficult for students, and that's why I really want to explain it in this setup video. So what is a radian? So here's the official definition. The radian measure of an angle in center position is the ratio of the length of the arc of a circle centered at the origin, subtended by that angle to the radius of that same circle. Okay, that definition right there blows the minds of a lot of students because they're just like, I have no idea what you just said. So let's break it down. So first it talks about having a circle centered at the origin. So there I drew a green circle centered at the origin. Then it talks about a radian being the ratio of the length of the arc subtended by that angle. Now that word subtended basically means that if we look at the angle that we have here, so let's say here is angle theta, right? We'll use theta to represent that angle. When that angle stopped right here, we created an arc, a subpart of the circle. Like, that's why it says an arc subtended by the angle, meaning that that arc or that angle cut out a piece of the circle, which is an arc. So it's a subpart of the circle, it's that arc. So a radian measurement is taking the ratio of that arc length to the radius. Everybody knows the radius of that circle. So we use a couple variables here. So we use S is the variable for arc length. Why they use S for arc length, I don't know. Maybe because S has a bunch of arcs in it because it's curved. I don't know. That's what I always think, right? So S is the arc length. Again, that subtended arc length. So when that angle stopped right here, we created that arc. So that length, right? That length we're calling S, and then everybody knows the radius, right? Here is the radius, or even here is the radius, right? The radius is always the distance from the center to the edge of the circle. So the ratio of that arc to that radius is the radian measurement. So that's how we measure radians. So we would say that angle theta in radians is the ratio, which is the division of that arc length S divided by the radius R. So S divided by R is how you calculate an angle's radian measurement. And you would say, well, why is this better than degrees? This sounds very confusing. Well, again, degrees is very arbitrary. Like somebody just made it up. Like it doesn't even, there's no rhyme to reason. But here we're actually connecting, hey, that angle, when it rotated to that terminal ray, it created an arc. And if we rotated more, we rotated less, then that arc would be bigger or smaller. But that length of that arc divided by the radius is how we can actually measure the size of that angle. And what's kind of cool is that even if we drew a smaller circle, because like I drew that green circle because I just needed a circle centered at the origin. But even if I made a smaller circle, I would have a smaller arc, but I would also have a smaller radius. But the ratio of that arc to that radius is the same. It would be equivalent to this bigger arc divided by this bigger radius, right? So even though it's a smaller circle, well, the arc is smaller, the radius is smaller, so the ratio between them is going to be the same. And I could do the same thing if I had a bigger circle. So look at this bigger brown circle. I have a bigger arc. I have a bigger radius, but if I take the length of that arc divided by the radius of that bigger circle, I'm going to get the same radian measurement of this angle. So this angle right here, that again I'm calling theta, regardless if I use a small purple circle, a medium green circle, or a large brown circle, the arc created, the subtended arc from that circle divided by the radius is going to be the same ratio, and that's going to be a very nice way that just connects, right? This is all making sense. And again, you might say, no, it's not making sense to me. Well, degrees make no sense. This makes far more sense when we think about how to actually measure an angle based on what that angle is creating, because that angle is creating an arc and it has a radius, and that ratio is going to be our radian measurement. Okay, so the next question a lot of people have is, okay, I've been raised understanding there's 360 degrees in a circle. Now you want to talk about radians. How many radians are in a circle? Well, let's think about this, right? If I take our understanding, right, vertex at 0, 0, initial ray, or on that positive x-axis, if I rotate all the way around one full circle, right, which you would know is 360 degrees. One full circle. How many radians is that? Well, let's use the definition of a radian. A radian, the measurement of that one huge angle, is the length of its arc divided by its radius. Okay, so what's the length of the arc? Well, this is a full circle, so it's the entire circle. It's all the way around. And what do we call the length all the way around a circle? You guys should know that is circumference. And the circumference of a circle is 2 pi r. That's the length of the arc of an entire circle. So if we take our formula, which is the arc length divided by the radius, so we take the arc length of an entire circle, 2 pi r, divided by the radius r, the first thing I notice is that those r's are going to cancel or reduce to a 1, and we just get 2 pi, which means that one full circle, regardless of the size of the circle, because the r's, the radius canceled, one full circle has 2 pi radians. Now notice I don't write radians after that. There actually is no unit on radians. We just say radians, but there's no inches, there's no degrees, there's nothing after it. It's just 2 pi radians. Now 2 pi is approximately 6.28. So there's approximately 6.28 radians in one full circle. And even if that circle was smaller, it doesn't matter. So let's just say that this was my circle. Sorry for my terrible circle there. But again, now what's the circumference of that circle? Well, it's still 2 pi r. What's the radius of that circle? Well, yeah, it's a smaller radius, so we'll call it r. But it doesn't matter because those r's are going to cancel, and I still get 2 pi radians. So no matter the size of the circle, small, big, medium, when you take the circumference, 2 pi r, and divide it by the r, the radiuses cancel, and we get 2 pi. So one full circle has 2 pi radians. So we need to stop thinking about 360 degrees in a circle and start thinking about 2 pi radians in a circle. All right, so what about a half a circle? Well, that should be easy. If a full circle has 2 pi radians, a half a circle should have pi radians. So all the way around is 2 pi, but if we just go a half a circle, like right there, that would be pi radians. Now check this out. Don't forget about negative angles, right? We could also go this way. That's a negative angle going going clockwise. That angle would be negative pi, right? It's still an angle, but it's going in that negative direction, so it would be negative pi. But again, that should make complete sense, right? All I did was I say, hey, let's just divide this by 2 because I'm looking at a half a circle. When you divide by 2, the 2's cancel and you get pi radians. So a half a circle that you guys should all know is 180 degrees is equivalent to pi radians. But I don't want to use degrees anymore. I want to understand a half a circle is pi. All right, now what about a quarter of a circle? A quarter of a circle would be going right to there. That would be positive 90 degrees, which everybody knows, but I don't want to use degrees anymore. So that would be a quarter of a circle, right? That'd be a quarter of a circle, right? Look at that. If you look at that like a piece of pizza, that'd be a quarter of the pi. So if we take a full circle, 2 pi radians, divide by 4, the 2 and 4 reduce to pi over 2. So that would be pi over 2 radians. Or I could do a negative, if I go down like this, that'd be negative quarter of a circle, or negative pi over 2. So don't forget about negative angles as well. Now we could also look at an eighth of a circle. An eighth of a circle would be if I split this up into 8 equal slices of pizza. So there's an eighth of a circle right there. So that would be simply dividing the 2 pi, a full circle, into 8ths. So 2 pi divided by 8 reduces to pi over 4. And I could even do a 12th of a circle. A 12th of a circle would be if I divide it into 12 slices. There'd be 1, there'd be 2, so there's 1, 2, 3, and then 4, 5, 6, 7, 8, 9, 10, 11, 12. So this right here would be about a 12th of a circle. So dividing this by 12 instead of 8. And if you take 2 pi, a full circle, 2 pi radians divided by 12, you get pi over 6. So basically, if we continue this breakdown, here is a rough picture of what we're looking at here. So we have pi over 6. That would be this first angle right there. Then we have pi over 4 radians. And then we have 2 pi over 6's, which would be pi over 3. So pi over 3 radians. And then here's that pi over 2. And we could keep going. And again, all the way, half a circle would be pi. All the way around would be 2 pi. Now, this means that 0 radians, right? That's an angle that didn't even budge. It's just didn't go up, didn't go down. 0 radians, so no angle, right? Would be a coterminal to 2 pi. So what I want you to do when you look at this is simply know how to count, right? Because a lot of kids understand degrees, and I don't want to use degrees anymore. I want to use this new thing called radians, and hopefully you're starting, and again, you're probably just starting to understand this, but if you could count, you could understand this, right? So we have 1/6, 2/6, which reduces to 1/3, 3/6, 3/6 reduces to 1/2, 4/6, that reduces to 2/3, 5/6, there's 6/6, right? 6/6, pi, 1 pi. So again, if you think about it in terms of pieces of pizza pie, oh my gosh, we could kind of connect pi there. We think about the fact that, in that first top part of the circle, right? In half of a circle, we could think of there's 6 slices of pie if we're counting by 6. 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6. And then we continue on 7, 6, 8, 6, 9, 6, that reduces to 3/2. 10, 6 reduces to 5/3. 11, 6, and then we get all the way to 12, 6. But guess what? 12, 6 would be full circle, 2 pi. We could also count by 4s. We have 1/4, 2/4, 3/4, 4/4. 4/4 would be pi. So if we're counting by 1/4, that would be splitting it up into fourths, which would be 4 pieces of pizza in a half a circle. Then we have 5/4, 6/4, which also reduces to 3/2, 7/4, and then 8/4. But guess what? 8/4 reduces to that 2 pi. So that's it. That's how simple it is. And obviously, you can say, well, couldn't you break it up by 14ths or 15ths or 16ths or 7ths or 5ths? Yes, but I wanted to break it down to nice values, right? If you talk about 2 pi, a full circle, breaking it down nicely, we think about 6/4 and so forth. So hopefully that makes sense. And again, I know this is brand new to you, but the most important thing you understand is how I'm coming up with these radian measurements. I'm thinking about the arc length that the angle creates and dividing it by its radius. So let's look at this one more time because I really want this to make sense. So if we have an angle right here, let's just call this, let's use a new value here. Let's just use theta again. Who cares, right? Theta is that angle. We could say, okay, here is the length of the arc that angle created. Here is the radius of that circle. And if I take that arc length S and I divide it by that radius R, I get the radian measurement. And that's why when we go back to here and we talk about, hey, this is pi over 6, all that means is that this arc length right here divided by this radius right here would be equivalent to pi over 6. That would be the ratio. All right, so again, the next step that we kind of want to think about here, logically going through this, is, okay, now that we understand the setup, standard position, vertex at 0, 0, initial ray, positive x-axis. We use these Greek letters like theta to represent this angle, and we know how to measure that angle based on this new radian measurement, which might take a little bit of time to get used to, but now we slowly start to understand that. We can understand one more aspect here. When we end a terminal ray, we end at a point. So right here, notice that we have a point P. So that ray ended right here. It created our arc. We divided that arc by a radius to get our radian measurement of our angle, but we also created a point in our XY coordinate plane. And all points in the XY coordinate plane have an X and a Y value. Bigger angle is going to be a different point. Smaller angle is going to be a different point. So again, if I said, no, I want my angle to be right here. I want a smaller angle. Well, that's going to be a different X and a different Y. Or maybe I want to rotate all the way into the third quadrant. Well, again, that's going to be a different X and a different Y. So we have a lot of things to connect here. And this is what trigonometry is all about, is connecting all this stuff together. So when we think about this angle, let me call this angle alpha, just use a different Greek letter. There's lots of things going on. First, we have the measurement of this angle. That's going to be taking this arc length, big arc length, there we'll just call it S, and dividing it by the radius of that circle. So that's going to be the radian measurement for angle alpha. But on this circle, we also have a point in this coordinate plane. You guys have been working with coordinate planes since you were kids, and that point has an X and has a Y. Now, finding that X and finding that Y is going to be super important to understanding sine, cosine, and tangent, the three big trig values. And I don't want to just jump and talk about what those three things are, because if you don't understand this setup, angle and standard position, the measuring of that angle in radians, and the understanding that that particular angle brought me to a particular point in that coordinate plane, then you're never going to understand sine, cosine, or tangent. So really, truly understanding this setup is really, really vital. So that's the end of this first part, right? And if we understand that setup, go back and watch this video again, right? Now that we understand this setup, we could understand the definitions of sine, cosine, and tangent, and they will be pivotal in helping us find that X and Y coordinate that I'm talking about, because trigonometry is the study of the three angles of a triangle. And to understand that, we have to connect all of this together. And it all starts with that setup that leads us to a point, and that point has an X and a Y. Different angles take us to different points. It's all connected through trigonometry. So pay attention, watch the next part that's going to really dive into the definitions of sine, cosine, and tangent that use everything I just talked about in this video.